right, guys. Thank you for coming to office hours again. You guys are like diehard office hours attendees. You guys are great, and you guys are helping out your fellow classmates in more ways than you realize. Just because what we do and record here, it's shared amongst your classmates, and they're able to benefit off of that. So thank you for being here. So what we're going to do today is just look at that enrichment problem that I posted, I think around 11:30 yesterday, 11:30 in the morning, yesterday morning. Did anyone get a chance to look at it? I also talked about it briefly during office hours as well. Did anyone get a chance to look at it? If not, I'm going to do a share screen to let you look at it again. Just take a minute, okay? So give me a second while I pull that up.
Morning, Mr. Chan.
Okay. Good morning, Michael.
Morning, Dylan. Did you see the edits I made to your doc? It was nice, though. I like it.
Thank you.
You're welcome. I really like it.
All right, so this was the
I like yours too.
This was the problem that I posted yesterday, okay? And if you recall, during office hours yesterday, we went over two different instances, okay, where we can have an inscribed angle inside of a circle, like I have shown here. The two instances were a situation like this, where one of the chord is a diameter and the other chord is on one side of the center of the circle. And then the second situation was we looked at two chords, both of which doesn't pass through the center of the circle. That leaves us with only one other possible scenario, okay, where we can form an inscribed angle inside of a circle, and that was this last one here that I posted for you guys yesterday. So we can have two chords on one side of the center of the circle, like so, okay. And the question is, okay, show that the angle formed here, that's inside of the inscribed angle, half of that of the intercepted arc. Okay. So everyone here clear with the
fellow munchkin cutting down?
Yes?
Yeah, I'm clear with it.
Yes.
All right. So
this is the one you did yesterday, right?
It's not quite like the one we did yesterday, although it is very, very similar. Okay. This is the third situation where you have to show and prove why that intercepted arc there is going to double the inscribed angle. What we proved yesterday were these two situations here. Okay.
Okay.
Like, is it a guarantee? Is it a guarantee that in this scenario here, it's going to end up with the same relationship? Well, I mean, you already sort of like know what the outcome is walking into this problem, because I'm telling you that's what it should be. But the question is, how do you prove that, right? Does that make sense?
Yep.
So again, this problem, it's a little above like what the regular weekly assignments are, just because this is enrichment. Okay. All right. So there was a trick, or maybe not so much a trick, but more of like a strategy. Okay. In proving things. Do you guys remember like what things we drew to help us out?
Isosceles triangles.
Yeah, we made isosceles triangles, primarily forming these isosceles triangles using the construction of a radius, right? So to help us out with the analysis, okay, this is what I drew here, and I encourage you guys to make this drawing as well. Okay, if you haven't done this yet, okay, I want you to take a sheet of paper. I want you to draw the circle, okay, and draw the situation. Here, I'm going to show the original problem again. Draw the situation out, okay? Draw the situation out. And again, we're going to prove. I'm going to erase this. Oops. I did not mean to do that. draw that diagram, okay? And then from there, we're going to try to, again, perform this analysis, right? So draw a circle and draw 2 chords like I have there, okay? Everybody have paper and pencil and things to work and write with? If not, I'm going to give everyone here 30 seconds to do that, okay? Everybody have this drawing made? Yes?
Give me 1 minute to draw it.
Okay.
I just got paper. Dude.
Everybody have this information here? The circle drawn and the 2 chords, plus the angle theta there? Michael, you have it?
I got it.
Dylan, you have it?
Yeah.
Kelvin, do you have it?
Yeah, I got it. I have a screenshot of it.
Okay. Okay. So if you have it, what I'm going to do with this, okay? Once you have the circle drawn and you have the 2 chords drawn in there, okay, and then as Emmett suggested, okay, the strategy was to form other kinds of relationships here, okay, that we can maybe possibly then construct other ideas. That's exactly what we're going to do. We are going to, again, approach in the manner that we did yesterday. So again, it's the same diagram, but this time we're connecting those points to the center of those points that are on the outside of the circle. These 3 points, we're connecting them to the center of the circle. Can everyone please draw that with me? Right, I need you to draw those 4 lines, those 4 dash lines. And by doing this, we've actually formed like 4 different smaller triangles. Do you guys see that? There are 4 smaller triangles that are formed, and not only that, we also end up with 2 isosceles triangles. What we're going to try to do with this, okay, is try to justify again that the angles formed here, in particular the angle over here, this angle theta, okay, is going to be half of this guy, half of the intercepted arc. That's what we're going to try to figure out. So let me know if you have this diagram drawn. Once you have it drawn, then I will go through and perform this derivation. So do we have this yet? Emmett, do you have the straw?
Yeah.
Okay. Dylan, do you have a straw? Michael, do you have this?
I'll take it now. This is an enrichment problem, right?
This is indeed an enrichment problem.
Because I feel like this is a more complex version of what I saw yesterday in Khan Academy.
That is exactly it, because you guys are slightly ahead of everyone else, which is why we're looking at this here.
Wow, that's cool.
Okay. Kian just
Okay, I got it.
Kian just walked in.
Yeah.
Morning, Kian.
Morning.
All right. Do you guys have this drawing made in your paper? Yes. Do you guys need another minute or no? Do you guys need another minute? So I'll take that as a no. All right. So what we're going to look at now, okay? Now that I've made this, now that I've made these instructions here, okay, we're going to try to
Let me finish the coffee.
If you look at this, what was that? If you look at this, okay, what do you notice about angle B here that I've made, right? How is this related with, how is this related with this guy right there? How are they related? Does anyone know? How is angle B related with theta and A?
Angle B and theta are congruent.
Angle A and theta are congruent?
B.
Angle B and theta are congruent. I don't agree with that statement. Why do you say angle theta and angle B is they're congruent?
Wow. Oh, angle B and theta plus A are congruent.
There you go. Okay. So again, why is that the case? Because we have this right triangle here. Let me draw it out for you guys, right? We have this right triangle over here. Not right triangle, what am I saying? We have this isosceles triangle. Okay? So in that isosceles triangle there will be the same as theta plus A. So that is a relationship that I will write down. You guys do the same. We know that B will equal to theta plus A. That is an important relationship to have. So I want to box this because we're going to come back to it. We will need to use this later on, okay? And you should too. You should box that. Are there other kinds of things that we can form from this? So for instance, what is the relationship between theta, D, and B? What do you guys notice about that? Do they have to add up to anything? Are they congruent? Are they equivalent? What do we know about theta, B, and D?
Ricardo, can you mute yourself? Yeah,
Yeah,
it
computer's kind of slow.
adds up to 180.
Thank you, Ty. That's great. So we have B. Whoops. So we can say that theta, whoops, plus B plus D will equal to 180. That is another relationship that we're going to come back to in a moment, okay? All right, another observation that I want you to make, I need you to observe closely here, okay? And that is this last triangle over here. So what is the relationship between C, D, and A? What is the relationship between C, D, and A? Are they going to be the same? Are any of those angles the same? Are any of those angles going to be complementary? Are any of those angles going to be supplementary? Do they add up to something? Like, tell me, what do you know about C, D, and A?
Well, C plus D plus A equals 180.
C plus D plus A also equals 180. Thank you, Emmett. So C plus D plus A, it too will equal to 180. Anytime that you don't know anything in math, right? The most important thing, and this goes with not just in math, actually, it's anything in life, right? If you don't know something, right, there is this mystery behind it. If you're able to name that unknown outright, that is the very, very first step of problem solving. So what we've just done is we've named things that we don't know. However, we are able to, from that initial step of naming the things unknown, naming the unknowns, we're able to then form other relationships, okay, between those unknowns. So now that we have these three things established, okay, the goal here, again, is to try to come up with, one more time, the relationship between theta and this arc. And it might not seem obvious right now, okay, how the theta and that arc is related, or how we're going to arrive at that conclusion. But let's see what we can do with this, okay? Based on your algebraic instincts, okay, things that you guys had studied in 9th grade or in 8th grade, okay, what do you guys remember? What do these things look like?
System
The
of
word
equations.
we're fishing for, it's two words. First letter is S, and the second word begins with the letter E.
A system of equations.
Exactly, Emmett. This is a systems of equations, okay? What I love about geometry problems, okay? Geometry, it's like it's a discipline on its own. But if you step outside of just these like textbook type problems, okay? Geometry and algebra, they're actually very much interconnected. We need algebra in order to solve more complicated like geometry problems. So yes, those two things, those two boxes that I have there, okay, those are systems of equations. And what does your algebraic instinct tell you to do when you have the system of equation, knowing that they both equal to 180? What does your instinct tell you to do?
Set them equal to each other.
Set them equal to one another because they both equal to 180, right? So a direct conclusion, a direct result of those two boxes, okay, what will end up happening is we're going to end up with this. So we'll end up with theta plus B plus D will equal to C plus D plus A. You guys okay with that?
Mm-hmm.
I'm okay with it, yeah.
Yeah? Okay. Everyone here clear with that arrangement, that substitution right now?
Yeah.
Yep.
Okay. So as a result of this, okay, the next step is, okay, we're going to try to come up with other relationships, okay? Wait a second here. Do you guys notice anything about this last equation that we wrote? Are there any things that we can eliminate?
Yeah, there's D on both sides.
There are D on both sides. I totally agree with that, Ty. So if I take this, okay, and further work with this, Ty, can you tell me what we end up with as a result?
We would get theta plus B equals C plus A.
Lovely. Love that. Okay. So we now transitioned into this. Notice right now, okay, again, keeping in mind what our original goal was, okay, this equation, the last thing that I wrote here, okay, it is still very much connected to the original diagram, okay? There's one other thing, though, okay? I'm just going to move this stuff from yesterday over because we don't need that at the moment. Give me a second while I move that. Let me see. I'll move this stuff. Whoops. I'm going to move all of this because we did that yesterday. Hold on. Okay. So we're at this stage right now, okay, where we have theta plus B is equal to C plus A. Have we used this information yet?
No.
We haven't, right? So let's try to utilize this. What can I do with that information now in connection with this last step?
Well, we know that theta plus B equals. Theta plus A equals B.
Theta plus. Say that one more time. We know.
So that means that we can write that. Yeah, theta plus A equals B. So
we can perform a direct substitution. Is that what you're trying to say?
yeah.
Yeah. So wait a minute. I can do this. I am just going to draw this guy. Whoops. I did not mean to do that. We can do this. Right? So I can do theta plus, what am I going to write in place of B?
Theta plus A.
Theta plus A, that's right, is equal to C plus A. And look what magically happens. And this is not an illusion or anything. What happens to the letter A?
They cancel out.
They cancel out. I'm left with 2 theta is equal to C. That's what I'm left with now. 2 theta is equal to C. Now, why is that important? Well, if you look back at this diagram over here, okay? Looking back at this, I called this center angle here C, didn't I?
Yes.
What would be this arc as a result?
C.
That would be C. That's right. This arc is indeed C. If that arc is C, wait a minute. What did we just find? That C, what did C equal to?
C equals to 2 theta.
2 theta. We've just proven the problem. We've just proved the problem here. So if you look at this, right, the proof was to show in any kind of situation, okay, and let me just walk you through again the process of what we had done in the past 2 days, okay, is anytime we have an inscribed angle, regardless of what the position of the chord is, whether it's to the left of this, left of the center, to the right of the center, whether both chords are on one side of the center or not, okay, or whether the chord passes through the center or not, that is not important, okay? That's irrelevant to the situation. That if this angle here is theta, what would be the intercepted arc again?
2 theta.
That would be 2 theta. That's exactly it. So let me just explain why is this concept important, okay? Because well, in about a week or so, okay, you guys are going to be doing more examples, okay, more problems related to this, directly related to this, okay? But there's a reason for why you guys study this, okay? So if you think about this, okay, I'm sure you guys maybe have been to like a ball game, or maybe have been to like a concert, or maybe have been inside of like a dome structure, right? Maybe the Capitol building. What do you guys notice about those types of like situations, those environments? What do you guys notice?
They're enclosed.
Okay, so one is they're enclosed. Okay, anything else that you guys notice?
Wouldn't the shape make an echo since it will bounce back from it?
That's
Like
right.
if you,
Okay. So any of those like dome structures, okay, a stadium, and an auditorium, okay, those environments are designed for those designs are the way it is for a reason, okay? And if you look at this, okay, mathematically, okay, this is an explanation for why auditoriums and stadiums and those dome structures are so good acoustically, okay? So imagine yourself, okay? Imagine yourself standing over here, right, at the edge of like, you know, the stage, okay? And you're speaking, okay? And you recognize that your voice is going to expand, okay? What's going to happen? What's going to happen over here where the audience is sitting?
You make twice the noise.
It would make twice the noise, right? This is mathematically showing why that phenomenon happens. That to me is extremely beautiful, and you know, it really just opens up like why like physical things happen in the world. Okay, so this again further explains, right? Regardless of where the person is positioned, okay, and regardless of where the audience is sitting, okay, no matter what, okay, they will always experience double of what that person is like the amount of sounds that they're making. They're always going to experience double it. Okay, you guys hear me?
Yeah.
yeah, I get it.
Oh, I'm sorry.
So that's why
The
it's
reason,
so loud in the back.
Like, can
No
you
problem.
show
The
like
reason-
the bottom part of the thing? I just want to see it.
say that one more time. I'm sorry.
Well, can you show like the bottom part of that equation? I just want to see it.
Sure.
Just,
Is my screen refreshing? Do you guys see it refreshing?
no.
It says page 12 of
Nope.
16, but that's it.
Okay, so you know what? I think I don't know why it's not refreshing. I'm just going to go back over here. I'm going to stop presenting, and I'm going to go back and present again.
Whoa.
Give me a second. Give me a second. Do you guys see my tablet or no?
No.
No.
I don't know why my tablet is not showing up. Give me another. I think I'm going to back out. I think I'm going to sign out on my tablet and then sign back in. Just give me a second.
Okay, sure. Do you guys hear echo when someone speaks or no?
Not really.
Okay, good.
Okay, I'm back in with my tablet. I'm going to go back in and present again. Okay, here we are. Oops. Here we are. So again, mathematically, okay, it's showing, again, why that phenomenon happens, okay? You know, as you study more math in the future, okay, whatever you guys decide to do, you know, to study other things in life, okay. For me, just talking about my personal experience, I always find that, you know, things always circle back to math, because, you know, whatever you study, okay, let it be like an English, history, you know, like the deeper you go, the more philosophical things get, right? The purest philosophy, in my opinion, right? You know, it gets down to just mathematics, because this explains everything in a very coherent and well, like in a very, very unbiased manner. Okay, just explains everything very, very nicely.
You mean in a very coherent and organized manner. That's what you meant to say, right, Mr. Chan?
That's right. That's right. Okay. Anyhow, so that right there, okay, is the proof for why. Okay, the inscribed angle is always going to be double the intercepted arc. I mean, half of the intercepted arc. Okay. Do you guys have any questions about this?
So yeah, I do have a question.
Sure. Go ahead.
So this theorem explains why if you're at the stage your voice is magnified because of the widening auditorium, right? Like,
This is so this theorem explains that, yes. Okay, but it's not like this theorem, its only use is for that. There are many, many, many different uses of this theorem. As a matter of fact, like your technology, like your CD-ROM technology, right?
okay.
You know how your CD-ROM runs? Okay, a disk inside of your CD drive. Okay, it spins, right, and then there's like a light that's pointed down on
Yep,
it,
laser.
right? Yeah, there's a laser that's pointed down on it. So in the field of optics, okay, this topic, okay, this idea of like inscribed angle theorem, okay, this whole circle geometry theorem, there are many, many, many applications, okay, behind it. Anytime you're dealing with light, any subject that you're dealing with light, any subject that you're dealing with acoustics, okay, you're going to be working with geometry, okay? But this is just like a stepping stone.
Wow, how incredible! And even video game characters are made out of like it's amazing how adjustable those triangles are.
Right. Okay.
I never knew that.
So again, in summary, right,
What do
these
you
are the
mean? What
three
do you mean?
scenarios.
Video game characters are made out of triangles.
I
Exactly.
like to watch it on YouTube. Like they're made up of tiny and tiny triangles. Like that's how actually facial recognition software works. It
They're
basically
made up of.
puts geometry on our faces to identify us.
There's geometry, there's geometry and generalizations that engineers and software engineers are able to make, okay, about a person's face, right? Facial recognition. There is a lot of geometry that's involved in that. Okay, that is true.
They're made of pixels.
Yeah,
Right.
exactly. Also, the picture.
So this right here, what I would do if I were you guys, okay, because I think I have a feeling, not I have a feeling, I know in the future, like these things that I just went through with you guys, okay, I would save the notes for this, okay, and then at a later point in time, either so about maybe a week from now, I'm going to ask people to take notes, okay, on this video. So don't throw those notes away, okay?
Okay,
Cool.
we won't. Yeah, sure, got it.
All All right. All right. I'm going to stop recording here.